Okay, so starting a series on another textbook called Regression and Other Stories by Gelman, Hill, and Batari, I think. So if you're not aware, these people are kind of major players in advancing the use of Bayesian statistics. This is a very good and approachable book. And so you can download a free version of the PDF here, and all of the course materials that you would need are here. Or if you prefer hard copies, you can purchase a hard copy. Okay, so we're in chapter 1, and so here is the question, and it's a long question, so I'll let you go to the Colab sheet and read it for yourself, and I will just paraphrase. But the idea, we're actually supposed to carry out an experiment, and there's some sample data that we're going to modify. But the idea is that we are going to take a piece of paper, a half piece of paper, and cut it and fold it in a way that it looks like a little helicopter, and then drop it several times and record how long it takes before it hits the ground. Okay, and further, we're going to do this many times with many pieces of paper, changing the dimensions of the helicopter. Okay, how wide the wings are, the length of the helicopter, and so we're going to have many data points. Okay, but I'm not going to actually do that. I'm not going to carry out the physical experiment. And so what I'm going to do is I'm going to take the sample data that they give, and I'm just going to modify it a little bit, and it will serve the purposes for this question here. Okay. So the first thing that we're supposed to do is to actually perform this experiment and record all of the data. Like I said, I'm not going to do that. I'm going to download data that they have available, and then I'm going to modify it. So you can download, I don't think you actually need this library. When I was trying to get it loaded, I loaded it here, but I won't delete it. So I'm going to download the data that they have available with this code here. Okay, and then instead of looking at, it only gives 2 different IDs, 2 different helicopters dropped several times, I am going to get many helicopters. Each row is going to be represented, or is going to represent a different helicopter. Okay, so here. And let's see, what else do I want to do? So instead of, so like I said, I'm going to have 20 helicopters, and I'm going to adjust the width of their wings and the length of their wings. And the way I'm going to do that, I'm going to take the original length, and I'm going to add or subtract some value between 0 and 1 centimeters, okay, in a systematic way. And then I'm also going to assume some kind of measurement error with this R norm, or not measurement error, but just imprecision in making these helicopters. So I've added a random component with a mean 0 and standard deviation 1. Okay. Actually, while I'm doing this, I'm going to modify this really quick. I'm going to make the standard deviation a little bit smaller. So let me pause here. Okay, so I'm back. So I've changed the standard deviations here just to constrain the size of the error a little bit. Okay, and then I'm also modifying the time of the helicopter, of the flight of the helicopter. And so I'm taking the original time that's given, I'm adding a random component, and then I'm also adding this component that is some function of the width and length. Okay, here it's a ratio, and in fact it's the cosine of that ratio. Or I mean, that's just what I'm doing to change the data. There's nothing special about this, other than well, I figure that the flight time is going to be somehow depend on this ratio, and I also don't think that it's going to depend in a linear way, and so I'm using cosine here to kind of combobulate it a little bit, discombobulate. Okay. So I run all of that, and so now I have modified data, although I'm not displaying it. And so now the next thing we want to do is to plot this in a way that seems reasonable. And so what I'm going to do is I'm going to plot the dimensions, length and width, along the x and y axis. And then I'm going to have all of these markers, and the size of those markers is going to represent how long the flight was. Okay, so let's just plot this. I don't know what it's going to look like now that I've adjusted these parameters, and rid we'll experiment a little bit as we go along. Whoa, that is way too close. So let me just get rid of that line there. Okay, so that's kind of interesting. So give me just 1 second. I'm going to pause again and do a little bit of experimentation. Okay, so I'm back. I didn't really change anything. But this is the plot that we get. So just in order to read this, let's kind of go along the x-axis. So as we adjust the width, okay, or if we go along the y-axis, as we adjust the length, if we go to a particular flight time, so here we have a flight time, okay, and so it was width about 5.3 and length about 7.95 or something like that, okay? And the duration of the flight was, abstractly represented by the size of this circle. Okay, so now given all of that, we need to find propose some dimensions that we think might be ideal. Okay, well, this is a little bit tough because, because the way that we have constructed our time, our time of the flight is this nonlinear function, and we see the consequences of that. There isn't really a clear linear pattern to what we have here. In fact, if I run this again, we'll get a different set of data. Okay. Anyway, it's not really clear where we would go that would be ideal, right? There's no discernible pattern, at least to my eye, where we are finding an optimal combination of length and width to find a pattern of the biggest circles here. Okay. We might think that if, as we go along this diagonal, I can see that most of the big circles kind of lie in this swath here. But that's also where we have most of the data, right? And so we don't really have a lot of data over here and over here. And so maybe the next thing I would propose to do is to build more helicopters that fill in these types of, or fill in these parts of the graph here, right, where we lack data, okay? But given the data that we have, it feels like about the best that we can do is to find the biggest circle, which it's not really clear where the biggest circle is here, but to simply propose that as our optimal ratio. Okay. So anyway, I think that might be the best that we can do in this circumstance. Okay,